So hello everyone. So yeah, today I'm going to talk to you about cluster cosmology and how machine learning could possibly help us do cosmology with clusters. So I'm going to do a very quick, I hope, introduction on cosmology, so on cluster cosmology, so that everyone is on the same page. So you all know that in order to constrain our cosmological model, we need to probe mainly two different sectors. The first one is the background evolution of the universe, so all the standard candle, the standard rulers, so essentially measuring distance in the universe and comparing it to our model. And the second sector is the so-called perturbation sector, which probes the growth of structure. And this is usually done by observing the large-scale structures via galaxy surveys. And the distribution of galaxies, the statistical properties of the distribution of galaxies depend on the underlying cosmological model. And the main probe that is usually exploited in those galaxy surveys is the two-point correlation function of galaxies. And some of you might be wondering why we never talk about the one-point correlation function of galaxies. Well, it's hard to do cosmology with that because galaxies are nonlinear objects and predicting all the nonlinear physics is quite hard, whereas the two-point correlation at large scale, it's much easier. So this is where clusters actually come into the picture. Clusters of galaxies are the largest gravitationally bound structure in the universe, so they are closer, let's say, to the linear regime, so it's easier to make prediction. They are due to their extreme nature, they are very sensitive to the growth of structure, to the growth history of structure, so it's a great probe of your model, especially of dark energy models. And since you are actually counting objects in a volume, it is affected by volume effect. So you're also probing both the perturbation sector and the background sector. So how do we use clusters in cosmology? It's pretty simple. You count them, and you compare those counts to theoretical counts. And we have a fairly robust framework for predicting the abundance of cluster as a function of mass and as a function of redshift since the 70s with the Press-Schachter formalism, and there has been iteration of this formalism, so we are fairly confident in this kind of prediction. However, like every probe in cosmology, there's challenges related to the use of cluster in cosmology. The first one being, what is actually a cluster? How do you detect a cluster in your data set? Because, for example, if I show you this picture, okay, the contrast is quite shitty, so it's even harder. But if I ask you, is there a cluster here and where is it? I would be very impressed if you managed to do it, and even I cannot do it. So this is the first challenge. How do you detect cluster in a galaxy survey? And the second challenge, which is, and not the least, is the fact that we can predict abundances as a function of mass, but the total mass of a cluster is not unobservable. Because, as you all know, most of the matter in the universe is in the form of dark matter, which you cannot directly observe or measure. So you always have to go through proxies of the total mass, and you also need scaling law that relates those proxies, like temperature, etc., that relates those proxies to the total mass, and that's a whole field in and of itself. And there is no consensus really on how to do this in a reliable way. So the idea of my talk and the work of I and my collaborator is to see how machine learning could possibly help us in tackling those challenges, both on exploring if neural network can help us detect clusters in galaxy surveys, and if neural networks can help us characterize clusters when we have detected them, like give us maybe directly their mass, give us their redshift, etc., etc. So to do this work, we needed data, training data. So as training data, we turn our heads towards the Sloan Digital Sky Survey, which is probably known by everyone in this room. It's a 20-year-old, it started 20 years ago with many different iteration and data release and so on. It's a fairly robust survey and very well trusted. So I'm just flashing on the screen the telescope here, which is in New Mexico in the US, and the footprint on the sky of this survey. So a 20-year-long survey. We used data from this survey, and more specifically, we used a catalog of 26,000 clusters which have been detected using an algorithm which is called redMaPPer. And the catalog contains the position, the redshift, and the richness estimates of those clusters. For those who don't know the richness, you can picture that as roughly the number of the number of galaxies in the cluster. And you have also the associated galaxy catalog, which contains all the member galaxies of those clusters with their position, their photometry, and so on. So this is just to show you what kind of data, how the data looks like. It's the same picture as before. So this is the kind of image that we are working with. It's the full resolution of the SDSS survey. So it's 0.4 arc second per pixel. So it's quite thin resolution. And we are working with 2048 times 2048 images. Those are JPEG, so there's 3 channels, red, green, blue. And those 3 channels are actually mapped on 3 of the 5 frequency band of SDSS, namely the I, R, and G frequency band. So this is our data set, 26-ish thousand images. And yeah, to answer the previous question, this is the same picture as before. And here, actually, the cluster is taking the full picture here, and the little red dots corresponds to the member galaxies of this cluster. It's quite a big cluster. There's like a few hundreds, couple of hundreds galaxies inside. So we use this. So this is for the data set, the training data set. And in terms of which neural network did we focus on, we focused on a convolutional neural network dedicated to object detection. But it's a network that was intentionally developed for real-time object detection, and which is called YOLO, which is an acronym for You Only Look Once. More precisely, we use the last iteration of this YOLO network made by the last one made by the original author. And the principle of this architecture is the following: it takes an image, subdivides it in a square grid. Which the number of little square can be controlled. And then it does 2 things at the same time. It predicts bounding boxes which you want to include the objects you want to detect. And at the same time, it uses the training set to train on assigning a probability of a class of objects. So in this picture, for example, we train a network to detect dogs, cars and bikes, and it's able to both at the same time being trained to find the boxes and assign the boxes to classes. And of course you can choose how many bounding boxes you have, and you have a confidence score associated to each box, and you have also a probability of all possible classes associated to the box. The architecture in more detail looks like this. So it's a series of a convolutional layer. The backbone is this darknet 53 block, which is made, as the name implies, of 53 convolutional layer, and that's the main feature extraction block. And then, as you can see, that's a feature of the 3rd version of YOLO. It makes detection at 3 different scales and concatenates the results. So it's quite good to, if you know you have several objects that have different size in your sample, which is kind of the case with clusters of galaxies. And at the end, as I said, you end up with a set of bounding boxes with position, size, and some probability score, and then the probability score for each of the classes. This is how it looks like if I apply it after training applied on the previous picture again. The truth is the yellow box, and the blue is the predicted box. You don't see it, but at the very top there's like a probability associated to it between 0 and 1. And so essentially this is the output that you get at the end. And so we trained our sample, and we then checked the performance of the final trained network. Just a quick precision. You can trade between precision and speed in this network architecture by playing with the input size of the model. And we played with 2 different input sizes, where the original 2048 images were rescaled either by a factor of 2 or by a factor of 4. And here you have the training and validation losses on each side of the graph. So this one is going to be more precise but slower, and this one is going to be slightly less precise but faster. So this is we explored a bit how the influence of this input size on depending on what we want to do with it. So this is for the losses. Now for the performance itself, here it's expressed as a function of the precision and the recall. Precision, in case you don't necessarily know what it means. Precision means essentially how much of the things you detect are actually true clusters. And the recall is among all the objects you want to detect, how many did you miss or how many did you actually catch in total. So you want the blue to be high as possible and the orange to be sorry, the opposite. You want both a high precision and a high recall ideally, but you have a trade-off between the two. And so this graph is maybe not easier to read, so you can actually plot those two quantities next to each other and try to find the point that is the closest to the upper right corner, which is the one that maximizes precision and purity, maximize precision and recall. And as you can see, we can get, especially on the high precision version of the network, you can reach a very high precision and recall of the order of 98%, which is very encouraging, and of course less for the less precise network. And if there's some cluster people in the room, you can there's a complete equivalence between the concept of precision and the concept of purity of the sample. And the recall is the same thing as the completeness. So the completeness purity is in the 98%, which is very encouraging. So essentially, the takeaway message is that we started with the idea of exploring how those kind of object detection network ready-made in the literature could apply to this kind of scientific problem. Sorry. So it seems like it can give both fast and accurate performance for cosmological application with clusters. So this opens up a whole new avenue of research for using this kind of networks in cluster detection, and especially it opens up the possibility for us, cluster scientists, to tweak those kind of network, to inject a bit of physics inside of it, and maybe tweak them to the different data sets that we have. Of course, just a quick caveat to keep in mind, the performance of this network ultimately is conditioned on the training sample, and here it's conditioned, that means it's conditioned on the original algorithm that we use to detect those clusters. So this is something to keep in mind. Eventually, we want to maybe move to other sample, to diversify the sample, and also possibly simulation, which might be the ultimate goal, but this has its own caveat. I'm just briefly mention something that I didn't have time to talk about, is the fact that we also add a secondary network at the end, a non-convolutional one, to do the characterization part of those galaxy cluster, redshift, mass, and so on. But I thank you for your attention, and if you have any question, we can discuss about it later.
Thank you so much. Okay, we have a first question from the audience.
Yeah, so it's Henry. I'm glad I'm no longer chairman, so I can ask questions. So, but is it actually better than a conventional way of finding clusters? I mean, you didn't really talk about comparing this technique with conventional, like redMaPPer or some other red sequence fitting technique.
So that's the thing. Since it's
why would I want to do this?
So so it was, in a way, a kind of a proof of concept to see if this kind of network can work. And as I said, we can do at most, we can do as better as redMaPPer, since we are using the training sample. There's a part of the paper that's going to happen, going to be published by the end of the, submitted by the end of the month, which is actually we are using another independent sample, like the Planck sample, and we are trying actually the completeness. We are still doing it, so we don't know yet. But we are using an X-ray sample and SZ sample to do an independent test of the completeness and purity.
Okay, thanks.
Okay, we have one more question for you.
Thank you, Stéphane. Yeah, I think I have also a related question, because I think the mean.
Mark.
It's okay?
No, yeah. So from Mark, that's
yeah. So yeah, the main caveat of this work indeed is that it's based on redMaPPer, so you cannot do better than that. So the question is, can you somehow, so the ones you fail on some objects, right? Because of your algorithm. So but the redMaPPer has some intrinsic errors. So did you check if the objects that you don't detect, your algorithm don't find, because are there some particular kind of objects that might be wrong by the redMaPPer, for example, or something like that? Did you check the properties of the ones you don't?
Yeah, that's the thing. That's basically the only part that remains to do. It's related to the completeness, purity on independent sample part. It seems to be potentially actually it kind of makes sense. It's the objects that it has most difficult time detecting are the ones that are slightly bigger than the maximum image size, so they kind of get away. So it's the cluster that are very low redshift and very big richness. So it seems to be those ones. We have less problem at higher redshift, and so they are well within the map, but it remains to be completely characterized, yeah, that's for sure. So at least we have an idea of where the thing fails, yeah.
Okay, thank you very much. So in the interest of time, we'll stop here for the questions. You have a few online, and I will encourage you to answer them. Thank you, everyone, and thanks again. Thank you.